I'm very glad to can talk about our recent progress here. I'd like to thank the organizer who invited me here. This is a really exciting workshop. You can see a lot of fast and exciting progress in this field. So today I will talk about some new tools for manipulating the rotation of ultracold polar molecules. So a simple technique to extend the coherence time of the rotation states in the dipole trap, so we can observe density-dependent coherence time, which is evidence of the dipolar interaction in the dark gas. Also, I will talk about some versatile rotation-dependent dipole trap in the second part, and our progress towards low entropy molecule in the lattice. Okay, so, okay, sorry. So, I think I don't need to give a very broad introduction. I just say, because you already hear a lot of exciting introductions. So, just say the molecule has so much rich internal degree of freedom, like electronic levels, vibration, rotation, and high-fan structure. So this is pose challenges, also opportunities to the researchers. For example, it was very hard to derive laser cooling molecules, but recent progress, just 5 years, you see a lot of laser cooled molecules, even in the tweezers and magnetic traps. Anyway, it's very promising, and the traditional way with a very high space density molecule create is by first make cold atom first, then associate them into the molecule, then ground state molecules. So this started with this Gila's pioneer work, and then a lot of different bialkyl molecules coming. So, and just recently, Gila achieved this degenerate Fermi gas molecule. That's really exciting moment. And there's a lot of unknown question like the inelastic collisions, because this chemical reaction on either the skeleton complex. So I will not talk about this too much. I just want to address this, how to manipulate these rotational states, and for quantum simulation and computation today. Okay, so our system is sodium-potassium molecules. So it's chemically stable and has a large dipole momentum. So there are a few groups can produce fermionic sodium-potassium molecules, including us. Also, Hanover group is very close to get this ground state bosonic sodium-potassium molecules. So our setup at MPQ started around 9 years ago. So it's a typical cold atom setup. After a lot of work and optimization, we can produce a double deep degenerate cold atoms with 10 to 5 sodium and 10 to 5 potassium with 20% Fermi temperature. So the dipole trap we are using is a dual color dipole trap, consists of a 10^4 nanometer and 15 nanometer dipole trap. This could be useful to identify this light assist decay on whatever, you know. And so after create a cold mixer of sodium and potassium, we use this radio frequency pulse transfer atoms into the bound state near the 90 Gauss resonance with -9.5 state. And typically we can produce 10,000 feldspar molecules. Okay. And so we develop a different scheme other than the MIT scheme. It's detune stirrup through this DD manifold. So the maximum single-way efficiency of the stirrup is about 50%. It's mainly limited by this laser noise, because the high-fan structure in the excited state, our scheme is not resolved. So we need to detune the pump light, so reduce the excitation loss. Anyway, we can routinely produce 5,000 ground state molecules in this high-fan state. Note, it's not ground high-fan state, but it's a vibrational ground state. and temperature about half microkelvin, and density is 4 times 10 to 11 per centimeter cube. We can also polarize the molecule with an electric field. It's up to half the Debye. Okay, so after create molecule, we measure this molecular loss. So indeed, we see a very clear two-body decay, and we can get this two-body decay coefficient is 7.6 10 to minus 11 per centimeter cube, with 500 nanokelvin. And the universal loss coefficient with P wave is 6 times 10 to minus 11. But MIT report is 4 times smaller. So the discrepancy probably because either the high-fan state is different on the calibration of the density on temperature has some systematic error. This, we cannot exclude this possibility. But you hear about a lot of this discussion of the sticky collision and two-body loss. So similar behavior has observed in the sodium rubidium and the rubidium cesium. So I think it's open question. So in the future, we definitely will try to clarify this more clearly. I just want to say, okay, because Taya's talk, I just say he gave this lifetime of molecule versus this trapping light intensity. So our trapping light intensity is about here. So it's still, if this is true, it's still light excitation dominated. So we don't observe a long lifetime, even with a 1550 nanometer here. Okay, so, but we can load the crate and produce the ground state molecule into a deep 3D lattice. We can extend the lifetime to about 3 seconds. You can see it's not two-body, instead exponential. This is mainly limited by this lattice technique noise. So, yeah. All right. So it's a good starting point to continue with this rotation manipulation. And I will introduce you the spin decouple magic trap. So this cartoon is made by our student Frog. It's just magic, whatever. So, you know, the rotation is a very appealing degree of freedom for control the dipole interaction, as you know from the other talks. Kaden also talked about that. So we want to use this, for example, two molecules can exchange their rotation, and this dipolar exchange interaction is long range, also anisotropic. Okay, this is very useful for the quantum simulation computation. And all right, so on the left, you need to know there are Molecular rotation structure. There are about 108 high-fan structure levels on top of this rotation. This will make the trapping in the dipole trap, so make long coherence time in the dipole trap rather difficult. So yesterday the speaker talked about this sweet state in the magnetic trap, which is insensitive to the magnetic trap. You can get 50 milliseconds with a very hot sample. But in the dipole trap, it will be rather difficult. I will show you later. So you know this. So this for this quantum simulation and computation, you need a very long coherence time. But you need a magic trap. So the two rotational states used as a pseudo spin for quantum simulation should feel the identical trapping potential. However, this anisotropic coupling between the trapping light field and the rotation make the trapping potential rather different. You need to tune the polarization of the light to a special angle. It's called magic polarization. So you can minimize the differential light shift to the first order. So you get a maximum coherence time here. It is limited by the second order differential light shift on dipole interaction. This is a pioneer work in GLA. And recently, so Duhan Group investigate this very beautiful nuclear spin, these high-fan LIBOs. So if you consider Molecular rotation, including these nuclear spins, there are like hundreds of high-fan LIBOs. They couple together. Also, they couple to rotation. So get this highly intensity-dependent transition frequency between the two rotational states. And this gives you a second-order differential light shift. And this limit this coherence time still to like 1 millisecond scale. But note that if you can trap molecule in the 3D lattice, you can cancel these inhomogeneous burning, and you get 100 millisecond coherence time. But this one molecule is frozen. But in the Barker gas, it's moving. This spin echo doesn't work well. So our setup, so before I introduce our simple technique, so want just show our setup a bit. So here, to investigate this spin decoupled magic trap, we use a 1D lattice with a 15 nanometer wavelength, trap the molecule in a few 2D layers, and we use 4 in-vacuum electrodes to generate horizontal electric field, and the light polarization can be controlled by the wave plate, so you can rotate to arbitrary angle between the light and the E field with a precision of half degree. And we use a dipole antenna to generate this microwave to manipulate the rotation. Okay, so first we measure this molecular rotation transition manifolds at very low electric field, and you can see this. We only show the strongest transition. There are hundreds of levels, so you can see these high-fan levels mixed together, and you can see the nice about the crossing. This in theory, this transition matrix elements. And in experiment, we also test that by sweep the magnetic field at a certain intensity across a small range. So every time when the sweeper cross the resonance, you see the atom molecule number drop. So basically, we map out this high-fan stack map. So certainly, you cannot work with such kind of so many states entangled. This immediately kill your coherence. So our simple technique is just turn on a small, moderate DC electric field, so you can split 1 plus or minus 1 state and 1 0 state in the excited state by the DC stack shift. Basically, you decouple this 1 0 state from the other rotational state, and you effectively decouple also the high-fan nuclear spin and the rotation. So you get a very clean level with very straight transition frequencies. Okay, so it's a very good two-level system and with very small curvature versus the intensity. Okay, and this is at the magic angle, as I mentioned. Sorry. So from now on, we just use this simplified level here. We measure this differential light shift with this particular level. So you can see this is the first order differential polarizability versus the light polarizability. And you can see this sweet point where this magic trapping potential to the first order. But if you zoom in this, so sorry, maybe I introduce how to measure this. To measure this, we measure the transition frequency versus the light intensity. And the slope give you the differential polarizability. So if you zoom in the magic angle, you can see the second order dependence. So with small electric field, this curvature is large. Eventually, this will limit your coherence time. So you can apply a higher electric field, reduce the second order dependence. We call it hyperpolarizability. Okay, to almost 0. So All right. And so, in principle, if you get high enough electric field and precise enough light polarization control, you can completely remove this differential light shift. Then your coherence time will be limited by the electric field inhomogeneity. So we spend some time on precisely control the electric field. So we use full vacuum electrodes, so it can generate near homogeneous electric field in two directions, at least. And the other 8 electrodes, they combine with the main electrodes. You have a three direction control of the gradient. So you can compensate the gradient in 3 directions and compensate to 0. Also, we use UV light to remove the charge accumulate on the glass cell. Also, we use very precise high voltage controller to control the electric field. So this is by the help of junior group. So we get maximum dephasing rate from the electric field, and the light is typically 30 Hertz. Okay. And then we just measure this with this very stable electric field and cancel the differential light shift. We measure the rotational coherence by Ramsey interferometry. So apply 2 half-pipe pulse and let it evolve. And when the evolution time is small, you see the contrast of the fringe, okay, is almost 100. But if you involve like a few milliseconds, contrast reduce, and this is contrast versus evolution time. And at very low density on small molecular number, we get about 9 millisecond coherence time without spin echo in the dark gas. If you increase the atom number, you saw this decoherence enhanced. Also, the shape kind of from Gaussian-like evolved to some exponential decay. And also, we tried spin echo. We found, okay, this coherence time can only extend to about 13 milliseconds. So why the spin echo cannot work in the trap? Because the particle is moving. So spin echo can only cancel those time constant inhomogeneity. So spin echo will fail when the evolution time is close to the trapping period. In our setup is 16 milliseconds. So let's limit our coherence time even with spin echo to about 16 milliseconds. And again, we saw this higher density, the shorter coherence time. And we map this dependence of the coherence time versus the initial molecular number. So also the density. You can see this coherence time drop with this density. And so when the molecular number is very low, this lifetime mixture of the 2 rotational states is 100 milliseconds. So let's not limit it by the collision loss. But when the density is very high, the lifetime is about 10 milliseconds. So I would say this is longer, maybe a bit comparable to this decoherence. So we use a very simple model to try to reproduce the experimental result. So we only consider this dipolar exchange interaction, also a homogeneous spatial dependent detuning of the microwave transition. So first, there are a few possibilities cause this dephasing of the decoherence. First, okay, you have this inhomogeneity, like gradients. And second, this electric field noise. If you have unbalanced loss, this reduces your T1. Also dipolar interactions. So we use a very simple model. So this is very powerful. It's developed by Cotton for the 3D lattice experiment of KRB. So we just use that, and the difference is our molecule is randomly distributed in a few layers. It's not don't have a concrete spacing here. Also, it's very hard to consider the loss and motion. So this is our approximation. This is really a bit difficult to consider this somehow. And we use this simplified model. So if we only consider the dipole interactions, it's the yellow line. It's certainly much longer. So the coherence maintain much longer than the result. But we know with low density, so the dipole interaction is negligible. From this, we know the inhomogeneous of the external field. From that, we can get effectively dephasing rate. So we add this one into the simulation. We can reproduce the observations. Also for spin echo, we get a smaller dephasing rate. We put them into the model. We can also reproduce these observations. So this indicates, so you consider dipole interaction between molecules, you can quantitatively describe this density-dependent decoherence. This is evidence of the dipole interaction in the Barker gas. But in the future, a theory considering the motion and loss are wanted. So I think this just because this extended coherence time, this make it now we require some more complicated, more complete theory about this. Okay. So any questions?
So what are the colors representing the lines again?
Oh, sorry. So this is data, of course, and the yellow line only consider the dipolar exchange interaction. And the black line, we add this effective dephasing rate. So yellow line is only is a simulation result, only consider dipole interaction, and the external field is homogeneous. And from the low density decoherence, we get this effective single particle dephasing. We introduce this, and we can, that's the black line.
I see. So then every single plot has the same dephasing.
Yes. Yeah.
So it has predicted power.
Yeah. So for this Ramsey, we use the same effective dephasing rate. For spin echo, it's smaller, but still, this part use the same dephasing rate. The spin echo reduce the dephasing rate. Okay, and we also consider if a density measurement is wrong by 50%, the dipolar decoherence still cannot explain this decoherence. That must be something else. This inhomogeneous field. Okay.
So this is somewhat related. Is the so how do you get your density that you use? You use the measured density, or you assume it's an equilibrium at a given temperature? How do you?
Well, we double check this. We measure the molecule number and temperature, trapping frequency. We calculate this. We also do an in situ imaging, get the size. They agree in a factor of 2. So
is there any fitting of those when you actually do these, or you're using the densities from other measurements?
The density is independent from the molecule number and trapping frequency, temperature measurement. And the only fitting is with the low density, we get effectively dephasing rate. Yeah. And we assume this just linear, this gradient external field. So just simplified simulation. Yeah. Okay, so guess not so much time. I just go on. So this is our very fresh results last week. So this versatile rotation dependent dipole trap. So so for quantum simulation, we want an arbitrary rotational dependent trap that would be very useful. For example, you can address some spin state without changing the other spin state. You have magic condition or anti-magic condition. This will be useful to generate some entanglement between particles. So there are a lot of proposals I just don't want to mention. So there's such an idea. We cooperate with Svetlana and Mingli. So we can use a highly rotational dependent transition here. So due to the selection rule of the transition, so here is the two rotational state. We want to do simulate quantum computation, and they couple to the excited state with different rotational state due to the selection rule. So J0 can only couple to J prime equal to 1 due to the selection rule, and J1 couple to 0 and 2. So with this, so you can generate a highly rotation-dependent dipole trap. But here, we need a very narrow line transition, so we reduce the photon scattering rate. So we use this from the ground state to the lowest excited state. It's a triplet state. In principle, the transition is forbidden, but due to the mixing between the B triplet and H singlet, there's still a kind of narrow line transition. The line width is about 0.7 kilohertz in theory. So anyway, and then with this highly rotation-dependent transition, J to 1 state, J to 0 state will fill the blue line. This polarizability on light shift versus the laser detuning is like this dispersion curve, and the J to 1 state, because it coupled to the other different rotational excited state, it generates complete different shifted transition. So here you can see there are a few special points, like here is the J to 1 light shift vanish, where J to 0 is finite. These two has the same transition, polarizability. It's a magic point. There's an anti-magic point. There's a tune out for J to 0 state and J to 1 state. So there are about 4 and 5 special points. So precision measurement of this special frequency can also improve the knowledge about this transition, but we have not done it yet. So we just measure this polarizability of J to 0 state by simply measure this stirrup two-photon detuning shift in presence of this we call it tune-out light. So from this light shift, and the calibrated light intensity, we know the polarizability of J to 0 state. It agrees well with the theory. And the error bar is merely because the calibration of the intensity is not so accurate. However, so because our stirrup laser drifted by 20 kilohertz per day, it's not so precise. So to measure J to 1 state, so essentially we measure the difference between J to 0 and J to 1 by using the microwave transition. This one, because we have very stable electric field and all the tools we developed for the magic trap, so we can precisely map out this differential polarizability. And here, around 10 gigahertz, you can see, okay, the polarizability changes sign. Here's a zero crossing, where this is a magic wave. So here again, we can create a kind of magic trap for polar molecules. So, yeah. And the last result is, so we also measure this lifetime near the magic wavelength. It's about 1 second. And the light shift is about 28 kilohertz. It's about 1.5 microkelvin. So it's this is measured in a deep 3D lattice. So any collision loss is frozen, is avoided. So the loss should be only due to the photon scattering from the trapping light. Okay, and we map out this decay rate. Decay rate is the lifetime inverse versus the detuning. Okay, we can see, okay, near resonance is just diverge. And, okay, but if you only consider from the ground state to the excited state excitation rate, you get a solid line, which is 10 times or even near 100 times smaller. This really unknown. The reason is really unknown, it's just preliminary results. So my guess is, okay, the spectrum of our TISAP laser has some, this fluorescence background. So this somehow give you a background loss here. And near the resonance, because we abruptly turn on the tune-out light to measure the lifetime, it could disturb the molecule in the 3D lattice and introduce more heating. And you can also note that near the tune-out frequency, the decay rate a bit smaller. That indicates maybe the abrupt turn on of the T-out light really enhance this loss. So this is really preliminary result. We will do more work, clarify this. Okay, so last, just talk about our progress towards this low entropy NUK molecules. So this pioneer work done in Gila and also in Innsbruck. So basically you create a double unit field insulator of 2 atoms in the lattice, and in principle you get exactly 1 pair of atoms each lattice site. You get perfect association efficiency of the feldspar molecules. So this is our progress towards this. So no one has demonstrated this scheme for the sodium potassium yet. So we are just progress towards this to make low entropy NUK molecules in the lattice. So we spent a few months to upgrade our setup so we can get a reasonably cold sodium and potassium before our atom number is 10 times smaller. And we also spend a few time to automatically load atoms into the lattice so we can get now the nice band mapping result of the potassium, also the superfluid to multi-insulator transition of sodium. So we also track the overlap between sodium and potassium by the spin exchange collision. So you can see the whole of the potassium is introduced by the sodium in the center of potassium. So this also, there's pioneer work in Gila paper. So next, before next, I want to show, okay, we also identify the zero scattering point of sodium and potassium by looking at, okay, after sympathetic cooling, we have most sodium remain. This indicate this zero scattering point. So this agree well with the quantum defect theory calculation by Yue Cui. So, sorry, I didn't put her name in yet. So next, we will optimize the sodium number and reduce the confinement so we have a unit field lattice. Sorry. And, right, investigate magnetic association. So in summary, we get this 1 Coherence time in the spin decoupled magic trap. Also, we get evidence of dipole interaction in the bark, and we demonstrate a versatile dipole trap. I would like to thank our team and also our collaborators, Ming and Svetlana. Also, this our new student. Especially, I would thank Christoph, who built and led the experiment. That's all. Thank you.